Alright, welcome to our second video of Unit 8. This one we're talking about all the different factors, at least the main ones, that affect our reaction rates. There are four main factors that affect our rates of reactions. As a reminder, rates of reactions are also called reaction rates, and they represent how quickly reactants are converted into products. So our first one is temperature. We'll talk quite a bit how temperature affects reaction rates. You probably have an idea. When you heat something up, does it seem to cook faster? Does it start moving faster? Does it move slower? That's what we're actually trying to be thinking of. Our second one is concentration. So when you put more of something together, will it actually react faster? Will it react slower? What happens when you actually concentrate something faster or more? Our third trend is the presence of a catalyst. We'll talk about what catalysts actually do, what they are, but especially how they affect our rate of reactions. Our final factor, though, I've been saying trend the whole time. Our final factor is the actual size of the individual particles. So, four main factors are temperature, concentration, catalysts, and particle size. Alright, here you go. In general, raising the temperature, we're going to start with that one, will speed up a reaction, and lowering the temperature will slow down a reaction. You know this. Common example is milk. You probably don't keep your milk outside the refrigerator, and if you do, stop. Just stop. Because milk basically will sour over time. There's some just compounds in them. That's kind of how milk works. And basically the process of its souring is an actual chemical reaction. To slow down that process, we lower its temperature by placing it in the refrigerator. Thus, it slows down the temperature and will slow down a reaction. And thus, our milk can last at least a little bit longer. As for why, with higher temperature, the individual particles have more kinetic energy. Hopefully you remember, temperature means average kinetic energy. And so, since these have more kinetic energy, they're moving around more, and they collide with more kinetic energy. Going back to collision theory, that says that if they're colliding with more energy, more of them are now going to have enough activation, or have sufficient energy to meet the activation energy, which means more particles will actually be able to react, and thus our reaction proceeds faster. And that's how temperature increases reaction rate. So, in terms of concentration, raising the concentration will speed up a reaction, and decreasing our concentration will slow down a reaction. An example of this would be burning wood out in the open air, like trying to burn a match, versus burning a match in a bottle of pure oxygen, if you will. Out in pure air, while air helps us breathe, most of it isn't oxygen, and so the flame will burn, just not that strong. If you put it in a vial of pure oxygen, the fire is going to burn really brightly. There's a lot more of the oxygen, which is one of the reactants, available, and thus our reaction will proceed faster. As for why, with a higher concentration, we have more particles in the same space moving around. Basically, in that same area around the fire, there's more oxygen molecules. Having more molecules means that a higher frequency of those are actually going to collide with each other, and more of those will actually collide with enough energy and orientation. Meaning, the more molecules we have, the more molecules will actually collide correctly, if you will, and thus the faster our reaction will occur. So we have a higher reaction rate. Okay, in terms of particle size, I know I said catalysts would come third, but I lied. Having a smaller particle size will speed up a reaction, and a larger particle size will slow down a reaction. Easiest way to think of this is when you're dissolving something in a drink. Okay, if you think of trying to dissolve, for example, a sugar cube, it's going to take a while to dissolve it. If you want it to dissolve faster, break it apart, get it into smaller sugar particles, and that dissolves a lot better. It's just breaking things down smaller enables more, well, you gotta learn surface area, so it proceeds faster. So the smaller the particle size, the higher the surface area that's reacting, which means we have more actual possible collisions. There's more places for them to react. So according to collision theory, we have a higher reaction rate. So basically what I tend to think of is a sugar cube versus sugar powder. On a sugar cube, we only really have this surface to react on. Whereas in sugar powder, we have all the surface area in between it. So that means each of those there's more area for a reaction to occur, more things to collide, and thus actually have a reaction. So our last one is the presence of a catalyst. Typically, the presence of a catalyst will make a reaction begin sooner, but it does not necessarily react faster once it's begun. It enables us to start the reaction sooner. It doesn't necessarily increase the rate overall once it's begun. Common example of this would be lighter fluid. Lighter fluid enables you to start a fire sooner, but it doesn't necessarily make a hotter fire per se. For example, if you're walking around fires, you're not really able to tell which fires were started with lighter fluid versus which fires were started without, assuming they're all burning a similar material. Because once the fire's kind of set and burning, it's just fire. It's around the same average temperature based on the ingredients. Just the lighter fluid won't really significantly raise that. A catalyst lowers activation energy. It's basically a compound that you use to make it, like I said, happen sooner. Going back to reaction profiles, the easiest way to see this. Let's pretend this is our basically reaction profile of a reaction. Okay, that means that our activation energy is from basically here to here. Okay, catalysts enable, if you go into AP Chem, it really enables a different path. It kind of lowers the activation energy, so instead you may have something like this with the catalyst. So you need less energy to start it. However, you still end up at the same point. You still have your reactants to products. Nothing really changes. It just is easier for it to start. That's the catalyst. So again, once the previous reaction has begun, if we have a catalyst, like it itself is not really going to increase things. You can increase concentration, you can increase temperature, but just the catalyst itself isn't going to directly change your rate. So as a reminder, our concentration or our temperature, if we increase it, will speed up a reaction. Decrease will slow it down. If we increase concentration, it'll speed it up. Decrease concentration will slow it down. If we have smaller particles, it'll speed it up. If we have bigger particles, it'll slow it down. And a catalyst enables us to start sooner, but doesn't really change what the rate's going to be. That's a summary and a reminder of our factors that affect reaction rates. Thanks for watching.